How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our very special business today has uncommon enchantment because the motion is beautiful to witness and wonderful to understand. We are going to talk about simple pendulums and other oscillating things. Consider the following. If we have a rigid support, and there are none really because everyone shakes however rigid, and we hang an ideal string. By an ideal string, I mean a string that has no mass, no weight, has no inertia, has no tension, is perfectly inelastic, ideal mathematically, and we hang a small bob on the end, and we displace it from this equilibrium position and let it go. It oscillates as a simple pendulum. Now, we wish to explore its motion. When you study the lesson in this business, you will find that the period, which is the time for a complete trip, comes out to be some such expression with which I will not have much to say, about which I will not have much to say. It's governed, as we see, by the square root of the length and depends upon where we time it. You know, for example, that G is one thing on the Earth and quite another thing on the moon. G is 32 feet per second on the Earth, but about 1/6 of that on the moon. As an incidental fact, matter, you would weigh, therefore, 1/6 as much on the moon as you weigh on the Earth. Now, I wish to do another pretty experiment with several pendulums. And I suppose maybe we could say pendula. This may be the plural of pendulum. Now, what am I going to do? I am going to hang up 3 of them, as I have them here soon to witness. 1, 2, 3. And how long are they going to be? This one is going to be 10 centimeters long, and this one 40 centimeters long, and this one 90 centimeters long. So the lengths are 10, 40, 90 centimeters. Notice the numbers, 10, 40, 90. I hope you get a little Q in there. There's 1, there's 4, there's 9, if we divide each one by 10. Now I am going to set them into oscillation. And I am going to count, say, 20 vibrations of each one. Here's the way I would do it. I would set this one into vibration, starting with 0, and here is a clock which I would start and stop, and I will just run one a moment to give you the cue. I would remind you parenthetically, I am not really giving you a lecture in physics. I am merely pointing out some things that you yourself can do with your teacher and even at home, and my purpose is singularly this, to invite your interest and stir your enthusiasm and curiosity, and point up at the same time the beauty and drama in these things. So I would start this 0, 0, 1, 2, 3, 4, and I would count 20 oscillations. And what would I get? Probably in this laboratory, I would get about 13 seconds. Now where you are, say Colorado on a high mountain, you would get a different time. And if you were in Australia, you would get a different time, because little g is different from place to place on the Earth. So I count 20 oscillations, and I get 13 seconds. Now I do it all over with this one. And I count 20 oscillations. And what would I get? I would get about 26 seconds. You thinking of something? Then I would do it with the 90 centimeter one. 0, 1. Oh, I should have stopped this thing because I'm not really clocking. Yeah, what's going on here? Huh. Well, there's something wrong with the... Notice now, this is the hazard we run when we depend on mechanical things. So I'm going to put the clock out of my sight. What would I do? Coming back here, somebody says, isn't the professor having a wonderful time with things going wrong? Sure they are. When you deal with nature, you must make her requirements absolutely perfect, or she will not do what you want done. So I count. I count 20 oscillations, and lo and behold, I get 39 seconds. Look, 10, 40, 90. They are in the ratio of 1 to 4 to 9. 13, 26, 39. They are in the ratio of 1 to 2 to 3. And now a marvelous thing is encountered. 1 is the square root of 1, 2 is the square root of 4, and 3 is the square root of 9. And that's what that so-called formula says, that the period is proportional to the square root of the length. And this other stuff comes out of some mathematical gymnastic. So we have learned a wonderful thing about pendulums by examining the motion of 3 of them. Now, strangely enough, when you make the exploration or develop the formula mathematically, notice that it does not contain, it says nothing about how big is the pendulum bob, how massive is it. All the period depends upon is its length. And you can show this by such an adventure as I have here. Here I have some pendula which are of identical length, let us say. Here is one made of brass, there is one of aluminum, there is one of cork, and we would find that if their lengths are identical, then their periods are identical. And that's a wonderful thing, because wouldn't you think that the heavier the bob, a different period would result? No, it does not. So we deal with simple pendula, pendulums, a bob on the end of a string. Now, anything can be a simple pendulum. Anything. Let me illustrate. Supposing you took me here, there I am, and you put a hook there in me, and you oscillated me. I am a pendulum, but not a simple one. I am a complex one. Or better physics language, I am a physical pendulum. A physical pendulum. And what is a physical pendulum? Anything that is not a simple pendulum. Illustration. Here is a metal rod. Now, if I put this on a support at one end and I oscillate it in a vertical plane, it has a certain period. It has a certain period. Now, remember, if it has a certain period, about an axis through one end, it has a certain time for its oscillation. Must there not be a simple pendulum which has the same period? Yes, indeed. A simple pendulum has the same period if it is so long. Now, how long is the simple pendulum that has the same period as this rod? Wonderful. If this rod is length L, the equivalent simple pendulum is 2/3 of L. So if I had a simple pendulum hanging here in this fashion, which was 2/3 as long as the rod, and I put them into oscillation together, they would stay in phase, meaning that they would keep step in step. So we speak of the equivalent simple pendulum as a simple pendulum which has the same period as the physical pendulum. Now, this is a rod, and this has a marvelous property. If I turn it around and put the axis at the 2/3 mark, and I oscillate it, it would be looking like this, of course, now. Here is the 2/3 mark. Here is a remarkable thing, absolutely enchanting. This rod has the same period for this axis as for this one. The same period. And hardly anybody ever believes that. But it is true, as you can discover by doing the experiment yourself. So now we explored a physical pendulum, which is a rod. How about a hoop? Here is a hoop. I have here a hoop, and I could support it by an axis about one edge, and I could let it oscillate in a vertical plane. I could let it oscillate in a vertical plane. Does it not have a certain period? Of course. It therefore has an equivalent simple pendulum. And how long is the equivalent simple pendulum? It is a marvelous thing to discover, but the equivalent simple pendulum has a length equal to the diameter of the hoop. So if you put a simple pendulum up here, which has this diameter, this length, they would keep in phase. Finally, how about a disc? Oh, a disc. Here is a uniform circular plate. And could I not support it on an axis in the manner as before and let it swing in its own plane? Supposing, well, I better draw a new picture. We are talking about a circular disc, a uniform circular plate, and I oscillated about one edge. What is the equivalent simple pendulum? Strangely enough, the equivalent simple pendulum is 3/4 of the diameter, a matter which you can explore by making some of these things yourself. Now, in addition to simple pendula, that's a bob on a string, and physical pendula, which are bodies of any shape, like rods and discs and hoops and the like, there are many other oscillating devices. Consider, for example, a spring. Here is a beautiful spring, nicely wound, so long when unloaded. I put a load on it, and I call your attention to the beautiful motion which it executes. That has a certain period in terms of the property of the spring. Now supposing I put a heavier load on it, a heavier load. Watch it. And I say that's a beautiful motion to experience, to witness. And now, the question, a beautiful question. Here is a spring of certain length and so stiff. Here is an identical spring which is only half as long. The question which arises is this. If the motion of this pendulum is so much with a certain load, what would be the motion of half the spring with the same load? And it is a wonderful thing to discover that it has, well, I'm not going to say. I'll leave it as something for you to explore, because I think it has much more virtue to leave some questions unanswered for you to explore than to just give you the answer. So I suggest you get a spring, indeed 2 springs, and explore their motions when one is twice as long as the other. And indeed you will notice that I have coupled springs in different ways, suggesting that their periodic motions depend upon how they are coupled. Regarding coupled pendula, look here. Here I have a pendulum, a heavy lead bob on the end of a rod, which is pretty nearly a simple pendulum, and here is another one. And I have, as we say, coupled them by putting a spring between them. And watch the marvelous behavior. I'm going to start one and let it swing, and we will see this enchantment. Its motion will soon die out, and the other one will take up the motion. Then that one will die out, and the other one will take up the motion. And this coupling of pendulums has much to do with electric circuits, about which we shall talk another time. But watch it. This one is going. That one is going more. Watch this one stop. That has practically stopped. Now this one is going to stop. It has practically stopped, and this one is going. And so we speak of coupled harmonic oscillators. Here is another pair. Here are 2 weights on very flexible rods. If I start one, we will discover a wonderful thing, that the motion of the first one is arrested and the energy is taken up by the second one. So, I urge you to explore the behavior of oscillating bodies, and I thank you for your attention.